I guess I'm responsible for. I just wanted to give a shorter talk because I have to leave to teach. But so I wanted to start with a story. There's a theorem that I have my theorem, which is that if you can't illustrate your talk entirely in emojis, then it's emojis and arrows, then you're doing something wrong. Your research is too complicated. So we have two scientists who each have some individual research labs which have their data sets. They're different colors, so you can see they're different. And what they like to do is they'd like to be able to collaborate. They'd like to set up a research collaboration in which they can learn jointly something from their two data sets. Right? That's a pretty reasonable thing to do. But maybe they're working in human health or some other field in which the data sets that they've gathered are sensitive or private in some way. So there's some difficulty. But assuming they can do this, then they can do a joint study and then get a paper and then get a prize or something for their paper that really managed to learn something that they couldn't have learned individually on their own because they've managed to collaborate and share their data. So this is a nice dream. This is the ideal world. Unfortunately, they live in a real world in which there are things preventing them, symbolized by this vampire and zombie, that are preventing them from establishing this research collaboration. So this cannot happen, in fact, or they cannot share their data in order to do this. So this actually happens a lot in human health research, mainly because the healthcare data and data from clinical trials or data from, say, neuroimaging studies, which is the field where I kind of connect to this, there's a lot of regulation around sharing that data. So who are these vampires and zombies, right? They're not actual necessarily individuals. They represent fears, legitimate fears, I would say, that researchers have about this data sharing process. They don't want to lose control of the data that they've gathered. That is, they don't want to just send you. I don't want to send you a DVD or give you access to a Dropbox with all of the MRIs of the people in my research study. That then you could just copy it and share. Who knows? Well, you'll put it on BitTorrent or something, right? There's a sort of more maybe this is the actual vampire and zombie here. They're lawyers at your institution who may have issues with you sharing your data, and then you'd have to have some kind of negotiation between the lawyers at your different institutions to hammer out a data use agreement. And then, of course, there's sort of ethical reasons where you gave a guarantee of confidentiality to the subjects in your research study. Perhaps you're doing a study on something like schizophrenia or Alzheimer's, early onset Alzheimer's or something like that, and you don't want to reveal, somehow there be an inadvertently reveal who was in the study to your research collaborator or to some other person at their institution. Right. But on the other hand, so that's like preventing people from collaborating, and then on the other side, there's a lot of pushes towards a lot of positives that can come out of collaboration, which are driving people to want to be able to do share or do some kind of collaboration with their private data. There are mandates from funding agencies. The NIH has a mandate on data that's gathered through studies that they fund that you have to be able to, that has to be accessible after, I think it's a year. You have a year to write all the papers you want to write, quick, and then you have to give people access to it. And then, of course, there's lots of new things you could learn, potential new things you could learn, and a lot of things you might want to learn are only going to be possible with data sets that are larger than you could get the NIH to give you money for. A typical Alzheimer's study using fMRI is maybe 50 subjects, so 25 cases, 25 controls or something like that, pretty small number. And you can learn some things from that, but if you want to learn from those MRIs, you would probably want more MRIs. And then the other thing is people are developing now sort of better platforms for hosting data in a secure way, or sharing some access to data, authenticating who's using it, who's getting it, and so on. So there's some, these are things which are helping people share. And so this last one that I mentioned, this ENIGMA project, is sort of the is the current state of the art in neuroimaging research. So there's a lot of work in neuroimaging trying to connect neuroimaging and genetics. So this is they've they won the acronym award here for getting a good acronym for their center. Very impressed. I mean, I aspire to do this kind of thing. So they want to understand brain structure, function, and disease based on this brain imaging and genetic data. And what they're focused on are meta-analyses. That's the MA, the meta-analyses. So these are analyses you can do with like already published information from these studies. They don't look at the raw data. They want to do that kind of analysis where they study post-hoc study conclusions. And the goals here are really to improve reproducibility and increase sample size for the kind of studies, findings you'd like to have. And there have been a lot of validations. There are many working groups on different health conditions, on different imaging modalities, and so on. So if you go to the website, you can see like all of the people involved. And so, for example, they can find genetic variations associated with certain neurophysiological conditions. So here's the workflow in the ENIGMA project, right? It is a Microsoft Office-based protocol. So what they do is to do a study with ENIGMA, which is like an agreement. People who join the consortium are agreeing to collaborate in this way. So you say, I'd like to do a study on some health condition, and I propose it to the managers of the ENIGMA system at USC, and they say, looks good, your protocol looks good. This seems like a worthwhile study. And then it says all the people who agree, who have data relevant to that study in the consortium, will then run some code that you've given them to on their data set to get some summary statistics like regression coefficients or something. They put it in an Excel spreadsheet, and then they email the Excel spreadsheet to the ENIGMA manager or the person running the study, and then they do some complicated Excel magic, or maybe they cut and paste it into, or they load it into R and do something in there. But this point is, this manager has to kind of perform this meta-analysis manually based on essentially numbers in a spreadsheet that were mailed to them. But despite this, what I'm sound like I'm being negative about it, it's really been a great success. So they had they have studies on aging in the brain, and this is a map actually of all the research labs or research groups that are participating in one ENIGMA study or another, and they're color coded by the different topics that they work on. And you can see it's really a global initiative. So the hope would be that we could do something better than just a meta-analysis, that maybe we can do some more complicated computations on the actual underlying data that they hold. So in order that, like ideally, in a sort of ideal world, we'd like to be able to simulate having all of the data in one place and just running the computation you want, but with just some more message passing, and everybody gets to keep control of their data. We'd also like some more formal privacy guarantees, and this is important, especially now that the GDPR has kicked in, and other privacy regulations kick in, that if we can provide some formal privacy guarantees, then you might enable some more people, international collaborators would be more willing to share data because everybody's on the same page. And also, if you can show that you have some success here, more people will see, oh, if I join in, then I can run a study on a bigger data set, and I can prove exciting results and get a ribbon, right? So this is all for the good. And so the theme for this talk, for however much time I have left to give it, is how to use differential privacy, or trying to argue or give a description of how differential privacy is really enabling these sort of research collaborations. That is, by providing that formal privacy guarantee that differential privacy gives, people will want to sort of share data or share access to their data because they feel more comfortable doing so. This is also, if you step back and you look at these two things, differential privacy and collaboration, you of course immediately think of Rebecca, right? Because obviously Rebecca works on differential privacy, right? And that's how we're working together. And because we're working together, she's also very collaborative. A lot of collaborations with Rebecca. So this is clearly a virtuous cycle, and really it goes both ways. And so you can really say that this nexus here really is the right stuff, right? So before I go on, I can just mention a couple of other projects, because then Dan is here. Some work that we've been doing on anomaly detection under privacy constraints with Dan. And then we're also looking at sort of putting differential privacy into like a system. And I put this figure in just because I know how much Rebecca dislikes this figure. And finds it confusing. So that's through a project, DARPA-funded project through the Brandeis program. All right. So what do people want to do, right? So what is differential privacy getting you? So research sites would like to collaborate and approximate some computation on their merged data. And so the first hack at this is, OK, well, I'll just sanitize my data. I'll somehow remove the things. Maybe I'll do it even better than just removing some features. I'll do some differentially private pre-processing, and then I'll just publish the data set, and then people can use that published data set. Now, this works in some contexts, can work pretty well in some contexts, but doesn't really work in this neuroimaging context, because the data sizes at each site are very small, are relatively small. So because of your small sample size, you are forced to live with a worse privacy guarantee to get anything useful. Or you get a reasonable privacy guarantee, but then what you can share isn't really useful enough to do something with. So really you'd like to have some kind of situation where you can do all of the machine learning, since I work on machine learning, all the machine learning things that you want to do, the exciting stuff like training, which people talk about a lot, and the less exciting stuff that people talk about less, like pre-processing and cross-validation. All the statistical things, you'd like to be able to do that on your private data. Now, the challenges here, of course, is that now instead of just like doing one thing, you have to come up with differentially private or privacy sense-preserving versions of all of these tasks, which is like, well, I guess it's good for writing more papers, but it's bad for getting fast progress. And then we need to, formally, so if you use differential privacy, we can sort of formally control the privacy risk from this process, right? And that's the benefit. So now I guess I have to define differential privacy for those the few people in the room who don't know it. I mean, I feel like Kobe should, since he's, he's the creator of differential privacy. He should really talk about it. But in differential privacy, you kind of imagine it's the way I'd like to describe it is that you're trying to confound an adversary who's trying to determine which of two worlds you might be living in. And there's a world in which your data set was X, and there's a world in which the data set was X prime, something that's very close to X. And so what you do, you imagine your algorithm, what it is it's taking your X and producing a Y. That's what algorithms do. They take an input and they produce an output, right? And this mapping is going to be done in a randomized way, so that the Y is actually a random variable whose distribution depends on the input data X. And so like the two distributions that you could get for Ys, these might be the two shapes of the two distributions, and you can see they're close to each other. That's the ideal. So what happens is, of course, you get a particular Y, right? The algorithm, whatever you run on which of these either of these two worlds, you're going to produce some Y, and that Y gets to go to some adversary, right? And then that adversary now has to tries to determine whether they were in the world X or the world X prime, and that difference between those two worlds tells them something about the underlying data. It tells them about the difference between those two worlds. Which world they're in, so they can try to form an estimate of which world they're in. And so what you want is you want to guarantee that these two distributions are close, and the way that you guarantee that they're close is through this formula here, which says that the probability assigned to an output under X and X prime, they're close to each other within this multiplicative factor e to the epsilon, and then there's this delta factor, which in paper I read recently was called the all bets are off parameter, which I've never heard before, but it was very appealing. Yeah, so you're not so not so happy with that. So what it is doing is actually it is in fact exactly controlling the false alarm and misdetection, or type 1 and type 2 errors for the problem of trying to guess which of X and X prime you're in. So this is really making a very strong statement about that hypothesis test. So how are we going to use this in this neuroimaging context, right? So first off, there's step 0, which I'm not talking about. You have to figure out how to express whatever your machine learning algorithm that you want to run on these brain images is. You have to figure out, how to what are the whys that the different sites have to create for you. And so instead of now emailing the manager, I mean, the same step 1 is actually kind of the same actually as the ENIGMA process. You'd email the manager and say, here's my study, but maybe you do it in a kind of more formally specified way. Here's the study I'd like to do on the neuroimaging data from all of the people in this consortium. If it's approved, then each site will compute in a differentially private way whatever aggregate it is that you want, the Ys that you want from them, and then A can put together the result. Now the thing is, the Ys that you can generate here, if you have a good differentially private algorithm, the Ys are more complicated, more rich, and more meaningful and more useful than the ones that you would be able to do in the ENIGMA model. And the reason that this works is that differential privacy has 2 very nice properties. One is called post-processing invariance, which means that once I produce, if I'm a site and I have my Alzheimer's MRIs here, and I produce a Y and send it off, I can then not care about what happens. I mean, I don't have to. If you go and run some function G on the Y, then I haven't lost any more privacy, as long as that G does not depend on my data that I have over here. And the other thing is that if you then ask me for something else, like tomorrow you say I want to run another study, I say, wow, you're really productive. Then I give you another output, this Y2, then the total privacy loss, the privacy risk that I experience, is the sum of the 2 privacy risks from each one. And that you can actually make stronger statements here if you use this delta parameter. You can make much stronger statements actually about how much privacy is lost. So this is great. This is great from a system design building perspective, because now you have a calculus for talking about privacy risk and saying, well, how much privacy risk have I taken on, and do I feel comfortable with that? Can I set a policy, and so on. And so this is why it's appealing from a system design perspective. So what do differentially private algorithms look like? They look like you put noise somewhere. You put randomness somewhere, so you put the noise somewhere. So the simplest example is I have a bunch of bits, 0 or 1, and I'd like to know the average number of ones, the fraction of ones in this set of bits. You can think of this as a state saying whether somebody is a drug user or not, or something like that, right? And then you do one of 2 things. You could have everybody. You could take every bit and flip it with a certain controlled probability, and that will mask the value of that bit to some degree. It'll create some uncertainty about what that private variable is, and then I could estimate. P hat. Estimate this P using this is a sort of plug-in estimator. This is a method called randomized response. And then the another thing you could do is, if you, instead of perturbing each of these bits individually, you could take the average that you want and then add noise to that. And if you choose the noise distribution correctly, then you can also guarantee this differential privacy guarantee. And the difference between these 2 approaches is quite large. The difference between perturbing, and this is the difference that I was mentioning before, the difference between like sanitizing your individual data versus allowing for some joint processing and computing the function that you want, in which case the average, the dependence of the error decreases, like goes from being 1 over n to 1 over n squared. So it buys you a lot if you if you make the computation of the average private versus sharing the sanitized bits. So where is differential privacy used in? Yeah.
Isn't R just p squared plus q squared? Or is P and Q defined different?
I'm expressing it this way because I'm expressing it this way to say, like, this is the number of number of ones times the number of people who said that in fact that their bit was 1, and this is the number of zeros.
I'm just making sure that I understand.
Yeah. The parameters are related, so the epsilon is a function of q, and if I wrote this all as a function of epsilon, this is a function of epsilon, it would start looking kind of ugly, and so I kind of kept it like this. Really, I should have just said O of n and O of n squared, 1 over n squared. That would have been easier. So where is differential privacy being used in practice? So a couple of implementations. One is Google trying to track some statistics from Chrome users, and then Apple has famously announced that they were putting differential privacy into iOS. Yeah, and nobody knew what that meant. But we have a little better sense of what that means now, thanks to some reverse engineering. And then the census is, famously, the census is going to be using differential privacy for the 2020 census. So that's exciting. But most of these things focus on counts and averages, very simple statistics, not regression, linear regression. So because I'm running out of time, I will kind of just briefly describe this system that we're trying to build, which we're calling the coin stack, which is built on this coin system, which is a system already for managing data for neuroimaging studies. So there's a lot of, it also is a large number of international collaborators, and they work on various conditions such as autism and so on. But here we don't have any, there's no method for automatic collaboration in this system. This is like a software system for storing your data in a nice uniform format and so on. And so we'd like to essentially enable collaboration with the data that's already in this system, that's already checked into the system. And because it's all been systematized in the same way, that becomes easier than sort of the ENIGMA model where everybody might have their local file formats and stuff like that. But the things that we want to do are much more complicated than averages and sums. You know, we want to do like principal component analysis or independent component analysis or non-negative matrix factorization and all of these sort of deep learning. Of course, I have to put deep learning on there because it's not a talk about machine learning unless you talk about deep learning. You know, but also basic things like classification and regression. And the other big challenge is that in any real analysis of MRI, there's a very long pipeline of steps that has to go through, that everybody has to run. So we're currently building this system, and like one example of how, let me just go here. So so sort of validation that we did of whether this system could work. We took data from schizophrenia studies and sort of that had already been merged together into one data set, and we artificially split it into sort of 10 made-up sites, each of which only had 25 MRIs. We had them to try and train a classifier based on those MRIs to distinguish between schizophrenics and non-schizophrenics. On their own, each site had something like a around 20+% error rate. But if instead what they did is they computed their local, they trained a regression model locally, shared that to an aggregator, then this aggregator could create a classification model which had something like 5% error, which is significantly better. So this shows that both the benefit of collaboration and sort of if differential privacy means that these people can collaborate, then they can really get something that's like much more significant and interesting than they could get on their own. They share the model only. So
it's bagging.
Yeah, it's like a form of bagging. So there's a big difference, you know, between this sort of, if you like, Google and Apple model, where you're kind of learning from, you can think of it as learning from phones or learning from browsers, versus like a system like this. And since I am out of time, I'm going to skip the next bit. But the idea is, but what the benefit here is that we learn a lot about how to put differential privacy into a system by trying to build these systems. And what I'd like to argue is that by building differential privacy into these kind of systems, we also learn a lot about problems that we should be solving as a more on the theory side. So so the question is, what did building this thing tell us? This building privacy protections into research systems like this really do give an incentive for more research to collaborate. We're actually now working with this very large study, it's a GIGA, Global Imaging Genetics Initiative in Europe for adolescents. We're setting up a demo with them right now to see if they can use this to do studies on mental health in adolescents. I didn't really get to talk about this, but if we have a sort of more generous trust model like you do in these collaborative research settings where you're not worried about the lab over there like really trying to exfiltrate your data directly, it lets us explore the space of differentially private algorithms, and especially the algorithms for more complicated tasks, machine learning tasks, to figure out what do we need to make them practically useful. And I guess the other thing we learned from this process is, what are some new and interesting theory questions? And this reason, of course, that I've bolded this is because these words are all things that, apply to Rebecca, right? So thanks, Rebecca, for all of everything you've done for me and for DIMACS and for the community. Thank you.